Hello students, welcome to EduCell. In this video, we are going to discuss about a local search problem which is named as Hopfield Neural Networks. So before going to the topic, I must tell you those who are new kindly watch the previous videos where we are planning to solve certain algorithms using certain techniques. In this video, basically we are targeting for the local search, how the Hopfield Neural Network is working, that we are going to discuss, as well as certain procedures, how the algorithm is approaches towards a solution that we are going to discuss also. And one more thing I must tell you that this content I have collected from Princeton University's PDF, which is being followed by the Tardos book, as well as I have also collected some important information from the book which is written by the Tardos and other co-author. Okay, so let us start with a Hopfield network. Basically, we should know what exactly it means. So, the basically we are going to use this Hopfield neural network in associative memory. So, before going towards that, we should somehow discuss about the associative memory. What is that? The associative memory is a type of memory which is you can correlate the random access memory or some sequential memory. These are kind of associative memory also a part of it. Okay, so kind of memory that we can use it. In general, whenever we are storing, as in a computer organization, I think you people have read, whenever we are storing in RAM or anywhere, suppose in a stored devices, in general register is a particular device through which we are just keeping the storing the data. Okay, so whenever we are storing, indirectly we are fetching the address of one particular segments, or might be the different types of segments within the memory. Okay, so based on the location we can find out based on the addresses. So through address, first we have to fetch the address, then we should store the data. This is the traditional way or in general way to store the data. Whenever we are focusing in associative memory, we are not focusing in addresses. No address we are keeping while storing it. Okay. So we are not focusing on address while storing. What exactly we are doing? We simply store by keeping the content or data directly stored without following any address. Okay, then why we are keeping this as good for neural network? By the way, neural network in general we are trying to get the data in time or might be with a less amount of time. That's why we are reading that one. The Hopfield is just one of them, which helps us to, whenever we store the data, certain pattern is getting generated. Through that pattern, it got stored in a register. So associative memory, the main advantage is, well, someone is searching at that time, the value will be displayed as quick as possible rather than the stored with the data which is being stored using the address or random access memory. Just think for that one. So if you're storing certain patterns, suppose has the best example I could tell you, like if you're remembering the registration number or you're remembering just a face, whichever is good, that the just storing the face is good, quite easier than the storing the registration number inside your brain. Like you can remember that one, for you it's good, but for others, how do you remember? Better you can remember the face of a person or a tone of a person. So while you are searching, like exactly whenever you have seen a person, so might be you can recognize him. So whenever we are doing a neural network, basically our target is to emphasize the performance of a system. Clear? So associative memory is a kind of memory through which we are storing a new data in a pattern format. We're storing that one. So other name of this one is also called as contention addressable memory. Content addressable memory, basically we are just keeping the contents, or you can say the data is addressed using the memory, so it is called as content addressable memory. Also it is named as that one. So the application, you can say, whenever we are searching the Google, okay, in a Google we are searching, so it's a parallel search. Whenever the people are searching, so we are getting a fraction of second. You can search anything in a Google, you will definitely see in the just above the tab, it will show you like how much second it took to give you the result. This many second, if it is getting reduced, means the maximum the correct output we are getting within less amount of time. This is what a complexity basically we are reducing. So the less complexity if you are following, so definitely we have to follow the parallel search, and the parallel search Hopfield network is kindly helpful in that. So this is a basic idea, we should go in detail. And definitely I must add the advantage as we have added. The disadvantage I must not tell is a disadvantage, but we should know. If I compare with the RAM, which is random access memory, definitely it is costlier enough. Associative memory is costlier enough than the random access memory or any other memories which you are using. Why? Because some logic gates are being used. Logic gates means you can say registers. There are a kind of registers we have to use. Well, match register, argument registers. Whenever you are searching something, it's a part of argument. It will be stored in the argument register. It will ask once you have got the match there, it will have to be matched in a match register. The different kind of registers are being attached means if the logic gates are more, definitely we can expect the price is more. This is in general. So that's why associative memory is costlier enough than the RAM. That's why we are in general we people are not affordable this one. So that's why we are just focusing on the RAM rather than associative memory. There are other details also. I don't want to go in detail about that one because this is just out of the syllabus. If I'll go in deeper, so just for a Hopfield network, why it is used, how it is being used, and what the application, that is I should have to tell you before going in detail about it. Okay, that's why I told it. Now we will go like in which we should focus here, like simple model for an associative memory. What is that? We have already introduced that one. Next, in which a large collection of units are connected by underlying network and neighboring units try to correlate with their states. Here they are focusing on the states. Okay, state of one age, or you can say here the input we should discuss. Then we can go in deeper, like how we can solve it. Like there is a graph V and E. V is a set of vertices, E set of edges for the graph with integer positive, negative, age weight. Okay, the weight we are going to assign to the age, there should be a positive or negative weight. That we have already discussed. It's a weighted graph basically we are discussing, which is a weighted undirected graph, you can say. Okay, the configuration is what then? Configuration is something we are going to configure through which the state, this represents state, under that it is written as u means state of u. State means you can say within that node, whether it is plus 1 or minus 1. Just based on the color we are discussing here, I'll be saying you which that color we are using as plus 1 minus 1. A state like this we are just defining. Okay, next, intuition, what we have to keep in mind, if WUV represents weight of age u and v, the age basically is having a definite two endpoints or end vertices. You can say u and v, the weight should be, if it is less than 0 means if it is negative. If it is negative, then uv want to have same state. Means if the age is negative, if here I'm just saying it a b, if I'm saying it is a negative which is minus 1, if it is negative, so the state, I must tell you the state means either if you can think with the color or you can think with the different aspects. If I'm saying it's a color, so both the color is white for them, or if you can say, if I'm saying the state, state can be represented as, state can be represented as color or number in the sense plus 1 or minus 1. Clear? That we are just discussing. If the color is white, let us think this is 1. So both the end should have the same color. Then we stop. This is what exactly the intuition means. Certain for best conditions for us, we should have to remember. Clear? If WV or W of UV means the weight is positive. If this is positive, so definitely the state must be different. If it is positive, I'm just writing here A this side, B this side. If I'm writing 1 as which is our positive value, so I must tell you one of them as it is white for both the end, at least one of them should have the change in color or a change in state. Instead of this one is, I'm just saying this one is 1 and this one is -1. This is just a state we are changing, or you can say in a color wise we are just changing it. This is intuition. This is an important point that we should know. Then what exactly we are going to find it out? In general, no configuration aspects for all the constants. You just think if it is a color, both, if there is a 7, 5, 6, both are positive, like all the edges which are there attached to each end points or edges or the vertices basically, these are positive in sense. So if I'm saying it's a positive, so either of the, suppose I'm focusing for this first stage, for the first stage there are two endpoints, but the based on the weight, if it is positive, so at least one of them will be having different color or different state. But here if I'm changing that to different color, suppose say this is red, I'm just changing for this edge. Again for this edge it is clear, not an issue, but whether it is correct, no. So the problem is if I'm changing the color for this one, so here it is not satisfying. So the main aim is to find a stable connections, or the connections or configurations basically which we are going to design, that should be stable one. Okay. So let us go in deeper exactly what and how we can say it's a stable one or not. First of all, we should keep in mind, like whenever we are going to configure certain things which is named as S, their ages or the age, if it is good, if it is said to be good, so the weight and the states, if we are picking of the same example I'm taking, if I'm picking this one is good for us, we should have to pick the states. How do we find the state? For this age, we have at least, as I told you, like it's white for us. If it is white, I'm just writing the note here through which you can easily understand this one. If it is white in color, so you just think it is +1. If you're changing, definitely the value will be changed. So you should keep this in mind. I'm just keeping as for the color. I'm just changing the state basically. Okay. Here you think the value inside it, because this is white. So here it is white. Then what exactly we have to find out whether this age is good or not for this node. For this node, suppose this is a U, this is V. This is our weight of UV. Clear? How do we find it is good or not? We have to multiply all this, like -1, which is our weight, WE, instead of WE you can say WUV. Okay, WUV into SU, which is state of U and state of V. So W of U is -1, here is 1, here is 1. The -1 +1 and +1, that you know, it's -1 is a value which is less than 0. If this condition satisfied, so we can say it's a good edge for us. For U, it's a good edge for the U. Again, if you're keeping the V as a U, then you can interchange that one, but the state should not be changed. Just change the U is a source for us, V is a vertices, which is destinations for us. So this in this way we can try to find out if it is less than 0, we can say it's good for us. Clear? Next, with respect to the configuration which we found, a node is satisfied. A node is satisfied, as we have discussed earlier, like how do we say if it's satisfied? If the weight incident to the vertex more good edges we are getting comparatively bad edges. Like the good edges is more than the bad edges which are incidents to a particular vertices. We must tell, we must say this the u which is that our target one, like here I am saying, here we are just focusing with one edge. Suppose here I am just drawing it a, b and c. Suppose here I am getting -1, here -1, here -1. Suppose towards this u, suppose I'm just focusing this one as u, you can multiply, you can definitely get the values. If you're getting these values are here for this, if I'm considering this is as u for us, next v, this is our w. So for this u, I'm just multiplying all this -1 into 1 into 1 plus, because this is one edge towards this and one edge towards this we are getting. So then -1 into 1 into 1. So definitely we are getting -2 if you add both this, which is 0. So we must tell that these are two different, two good edges, two good edges towards the u. Clear? This is what we can expect as our value, which is -2. We are expecting after combining this one -2, which is less than 0. Clear? So these are two good edges for us. Good edges for us. Next is a configuration is called as stable if all the nodes are satisfied. Clear? So the satisfies, we can say if it is less than 0, we can say a node is satisfied. If all the nodes are satisfied, then we are saying it is stable, and our aim is to find out a stable node basically. Clear? This is what our target is. Just an example I have just kept for you. So initially it is not like this. Initially you can say a color has been kept by this 4. Here it is -10. Here it is 0. Here it is -5. Here it is -1. Here it is -1. Initially all are white. Okay. So as we know, for this age, both the states are good. So don't worry about this one. Here -1 as an age, so definitely all the states are at same state, which I have already discussed with you. Like if the age is minus or negative, so both the endpoint should have same state. In the color, you just focus on the color only. So if I'm saying with this -5, it is -5. If I'm saying this, both the color are same. If it is -10, both the color are same. No need to worry about. The main objective we are finding out for the 4, if we are taking the positive hit of that one, the age, so definitely the state should be different. So here, if I am taking this one as I'm just coloring, suppose I'm coloring here, which is done here only. After coloring this as black, once it is done, so how do we say, like what should, like whether it is satisfied or not, how do we find it out? The main aim is to collect all the informations like this. I'm just writing it here. The incident edges. There are 4 incident edges to a particular node. Then as per this rule, how do we find 4 into, as we have said this as just color has been changed to black. As for this, the black is -1, white is +1. Here I'm just highlighting this color as yellow. You just think it's -1. So -1 as a one state, and the state is 1. Then another edge, this is one edge. Another edge is -5, -5 into -1 into 1. Next plus, here is -1 into -1 into 1 you are getting, and there is -1 into -1 into 1 you are getting. So in this, what exactly you can find it out, the total calculation whatever that you are getting is 4 minus 4 plus 5, then plus 1, then plus 1. But the problem, what exactly we are getting it here is, if I am picking this one, in general, what the people are actually doing the mistake that I'm telling you. If I'm saying this one to be changed, I should have to keep always in mind. I should have to write this as note 2. Don't forget to change the single node first. This is what I want to tell you. If I'm saying this one, so indirectly what you are getting, so by the way, you are getting this as not satisfied. I'm just saying you this one. But basically, it's not a good idea if you're just picking directly a middle point of it. It's not a good idea, by the way. If you're taking just for one reason, we're just discussing. Okay. So if I'm just coloring it, you can say minus 4, and this side is minus 7, sorry 7, which is 3. 3 is greater than 0, which is not satisfied. So there will be a problem we occurred here. The main issue exactly, whenever we are fixing off with a color, we should first focusing on the single node which are getting connected. Here we have done a mistake because we have never gone to the single node. We have just followed the other nodes. The first target is, if you are picking with the color you are getting changed, so your target should be the immediate which are connected, the single one which is connected, you should focus there. So as we know the negative weight, if it is assigned, so definitely the state will be same for it. Okay, so you should change the color accordingly. Here the color has to be changed, here the color has to be changed. Once it is done, then you focus whether it is satisfied or not. Then I'll tell the algorithm. Algorithm is something different. Previously we are not following any algorithm, then how do we find it whether it is satisfied or not? That is we are discussing. After using the algorithm, you will definitely get it thoroughly, like how it is working. So once the single endpoint is done, step single should be single edge, a single connected edge must be, I am writing connected edge should be checked first. Once it is done, then only you can go to other side. Once I am doing this one, so at this side, instead of plus 1, I am saying it is minus 1. Here I am saying it is minus 1. Then I will be getting, instead of plus 1, I am getting 1, minus 1, minus 1. So here one side is plus 5, another side is minus 6, which is less than a 0, you can say. Less than 0 means it is satisfied. Once it is satisfied, we can get the value and we just color as for this one. But one thing we should remember, how do we say which one is bad edge for us or which one is a good edge for us? This is positive and the states are different. We can say it is good edge. And for minus or negative one, the states are same. Negative, the states are same. So I must tell this one is our good edges. Okay, and this one is said to be bad edges. Why? Because minus is here, but the states are different. This should not be different, but it is here we are getting as a state is different. Clear? So here, how do we say it's satisfied? Again, I'm just saying incident good edges are more than or equivalent to the bad edges. For this vertex, there are 3 good edges, 1 bad edge. Definitely good is more. That's why we say is satisfied. Clear? In this condition, we should say it is satisfied. If you say, sir, why not this one to be picked as one of them, as one of the good choice for us? Just think over it, now. If you're just thinking like this is 1, this is 1, this is minus 1. For this, there are 2 different edges are coming. For this one is minus 10. Why? Because 1 is there, 1 is there. So I'm just directly multiplying this one minus 10. Here is minus 1, minus 5 is 5, then plus 1. So the ultimatum is minus 5 is less than 0, so it is satisfied. As well as if you can think it's a bad edge, it's a good edge. So it is equivalent, no? One good edge and one bad edge, as it is there, good edge equivalent to bad edge is also considered, but good edge should be more than the bad edge if you are saying a node is satisfied. Clear? So if all the nodes are satisfied, then we say the configuration which we have done is stable one. A stable is our Hopfield network. Clear? This is what our idea is. I hope it is clearly understood by you. Next, we are following, like, how do we find a really stable one? The goal is find a stable configuration if such configuration exists. Clear? Next, a state flipping algorithm we are going to use, where we are just flipping the state. Flipping in the sense, you can say switching the state, a color, the different color we are representing, but our main target is, we have already informed, like, we have two colors we are going to use. One is white and another is black, through which it is clearly understood by us, like, white is considered as 1, so suppose black is -1. So in this way, if you're changing the value, once again I'm telling you, instead of 1 -1, if you're just changing this value, definitely the value will be changed. The representation will be changed. Now the value will be changed, it's a representation will be changed. You should keep in mind before changing that one. Okay. Next, we are following S here as an arbitrary configuration we just has taken already. Next, based on the configuration, we have to run the while loop. What exactly we are doing? Current configuration, whichever the configuration that you have taken, if it is not stable in the sense the nodes are not satisfied. If not, then what you have to do? You have to focus the unsatisfied nodes. You suppose an unsatisfied node you have taken, then what you have to do, you just change the state. You have to change the state. Change the state of the selected node, which is said to be you. Clear? How it is clearly understood by you, how the algorithm is there. Based on the example, we can easily understand. This is the example there in a book, so I kept it. No, the PPT also I kept it. So here initially the figure is like this, a configuration, basically we can say it's a configuration, A said to be configuration, where black is already being fixed. And I must tell you here as a note, the same thing I am writing here, white is said to be 1 plus 1, I am just writing it here, black we are representing is -1, and note, this is note 1 and note 2 is, we will be initially we should be focusing with the single connected edge will be picked first. Okay, so whenever we are picking, the single connected edge will be picked first. Next, you should focus here how to check the satisfiable condition. As we have already seen, there are two different incident edges. Based on the incident edges, this is our -1, this is our +1. For this particular configuration I'm discussing, next onward you can easily understand. Here is -1. For getting this whether it is satisfied or not, how do we find? There are two different edges. For this edge, suppose these are I'm just writing it here. For this edge, the value will be -10, which is the weight of it, and -1, one of the state of it, which is u, and one of the state is this one. Clear? Another state is, another edge which is inclined to this is 8, is a weight of it, and -1 is the state of u, and the state is 1. So in this way what we got, 10, other side is 8, whether it is less than 0 or not. If it is not less than 0, no, so we can say it is unsatisfied. So here we are getting 2, which is greater than 0, so it is unsatisfied. if it is unsatisfied, what we said, it is unsatisfied, we should change the state. Change the state means instead of -1 we're changing it to 1. Now it is 1, we changed it to 1. This is now 1. Clear? I hope it is clearly understood by you. Instead of that, we're changing it because that was unsatisfied. Next, we can switch to this one. Here we can say it is 1, it is 1. Here is also 1. So there are two incident edges for this node. So we can say -10. I'm just directly writing it. -10. Why? Because 1 into -10 into 1 equal to -10. Here 1 -4, 1 -4, which is -14. -14 is 0. So it is satisfied. Satisfied. Don't worry about this one. If it is satisfied, you let it be, like you forgotten what you have done. Next, exactly as for the example, the previously it was black, so we should focus on the black first. Then you can focus other nodes also, not an issue. So if black is given to you, like we can check whether it is satisfied or not. We have to check that one. To check whether it is satisfied or not, by the way, we know if it is a single edge, don't worry about anything. If it is single edge, you have to check the weight. Weight is minus, means negative. Both the states should be same, but here the one state is different and the state is different, so you can just remove that one. But as for the formula, if you want to put that formula, if you can say no sir, we have to follow the formula, you can follow that one, not an issue. If you're following this one, -1, which is the weight of this age, into state of u, and the state is 1, so you can say 1 which is greater than 0. So greater than 0 is unsatisfied. If it is unsatisfied, you need to change that one. What you have to change? You need to change the color or the weight, stable, state of that one. As to color might be changed, or indirectly we are changing the number inside it. Okay. Next, once it is done, so this node, if you are picking this, so based on this, the previously all are 1. So if all are 1, so here no need to worry, 8, then 1 this side and -4, -1, -1. So you just check whether it is satisfied or not. So definitely we are getting this is -6 and 8, which is be 2. 2 is greater than 0. So we can change the state. State change, initially it was 0, or sorry, it was white, which is +1. It changed to -1. Okay. So next, for this one, if you want to pick, as it is a single node, don't worry about that one. If you are following the formula also, the formula will definitely give you the correct result. But for a single, always you should keep in mind, if it is negative, both the states should be same. If it is black, so definitely it will be black. Again, for this one is also black. This said it is stable, means this is we got using the state filling, or you can say flipping algorithm, because we are changing the state of it, and we are indirectly flipping the states to 1 to -1, like this we are getting it. So I hope you clearly understood this one, and it runs within a polynomial time. We will be discussing that one too here. Theorem says a state flipping algorithm terminates the stable configuration at most this one, like the edges which we are having, the w represents the maximum, at least that one we can be iterating this one. Okay, so how do we prove then? This phi is basically what it says. You can say it's a configuration which we got. It's a good configuration, which is satisfiable configuration for us, which set all the edges which are to be good. Here it is also said as the good edges are getting considered first. These many things are being given to phi of s. Next, clearly which says 0, then after that phi of s, then after that it will be within this range or not. How do we find? We have to just check it. So phi of s increases by at least 1 after each flip, that we will be discussing. These are certain things to be discussed after proving this one. So how do we prove? U flips a state, means suppose a state is getting flipped, you can say instead of black, if it is white. So if I'm changing any state now, so definitely the good edge become bad edge. So here it was good edge. Okay, suppose I was there, like here it's a good edge for this one. both the states are good, both the states are in the same state for this -1. If I change to black na, so here it is good. Why? Because states are different. Here states are for this one, this example for C to F, you just focus. Initially it was a white, it was white. So both are in a same state. But here there is a problem in a bad age. Here there is a good age, good age. When you change the state, now what it finds, this is good, this is good, and this is good. This is a bad. Why? Because the negative is there, and we are getting the values are different states. So definitely we can say if state u is different, means you flip it, means you change it, so you become bad, the age, the good age become bad age, the bad age become good age. So like how do we find this represents as unsatisfiable, as it is written like unsatisfied and flip state is considered by this one, which is being said to be you know phi s dash. This is written here. That's why I kept this content from the book. This side, the right hand side, I kept from the book. This side I collected from the PPT. So this one is our good one, which is our stable condition, because which we found using the good edges. Next, this one is like those all the edges which are there, which are the bad edges and the certain good edges. If you're finding out if it is unstable, always as per the book, it is G stands for GU and BU. BU stands for the bad edges, GU stands for the good edges. So I'm just writing here as good edges. This is for the bad edges. So in general, if you are just making it unsatisfied, if it is unsatisfied means, as I have told you, if it is satisfied means the good edges will be more. If it is unsatisfied, just opposite to that, bad edges will be more. So here they have written if S is unsatisfied, then we can say uh, bad edges is more than the good edges. So in that case, if you are just following this formula, what we are getting, like for the good edges, if you are just making that one to bad edges, you can get the bad edges is more than, like more than the good edges. So in that case, like we can say, as per this one, suppose I am following the conditions to be written as phi s dash, suppose I am finding. So in this case, phi s dash, then phi s, then as you are following this formula, so where the good edges is GU is a good edges, then is good edges plus 1. So good edges will be cancelled. Why? Because in place of bad edges you put good edges there, because bad edges is more. If it is more, just at least one time more, so we are just considering that one. Then after that, what you got the value as phi s dash, which is unsatisfiable or unsatisfied one, it is satisfied plus 1. This is what the result we got. Or this side I'm just writing, might be it is not visible, so here I'm just writing phi s dash. Now we are getting as our value like s plus 1. Okay, this is what we got as our result. So it is, as I told you, it's a polynomial time we are getting as a value. So I hope it is clearly understood by you. If any doubt you are following, so please comment below. Have a good day.